In the previous lecture, we started the discussion on RF power dividers, and in the course of doing so, we looked at one configuration of a power divider, and that is the resistive power divider. So what we saw was it is a symmetric circuit, three ways. That is to say, there are three branches, each corresponding to one port, and the fact that the circuit consists of resistors, it is a lossy power divider, but it is reciprocal and it could be made matched also. So as we had established in the previous lecture, that it is impossible for all the three conditions, that is of losslessness, matching and reciprocity, to satisfy all at the same time for three port networks. At the same time, along with all this, we want that the power divider should also be able to act like a combiner. That is to say, it should be reciprocal also. At the same time, all the ports should be matched and it should be lossless. So therefore, we need these conditions. At the same time, we know that there is a bound imposed by nature. It's not possible. So therefore, the question is, how close can we come? How close can we come to satisfying all these three conditions? We have seen one case where we could get matched and we could get the reciprocal circuit, but it is lossy. So we know that at the most 2 out of 3 we could satisfy. But the question is there something we can do better? Well, let us first see how to overcome the loss in case of the power divider. So the first thing when we say about the lossless power divider is that there should be no resistors. So in that case, one thing that we can very easily do is that, let's suppose there's a wire and there is some current flowing over here, I, and with respect to ground, the voltage over here is V. Suppose this voltage source is able to supply the current in this direction. So therefore, if we now connect two wires over here and sort of terminate them with resistors which are equal value, then in that case what will happen is that the current will be split into two equal parts. At the same time, the voltage over here is V. I am giving this example purely from a circuit point of view. For the time being, let us not assume anything about transmission lines. So even if this is a DC voltage, we can say for sure that while the current gets split into half, the voltage at the junction does not change. So therefore, the power entering will be equal to V times I, the power entering the network. And the power that is being delivered to each of the two loads will be V times I by 2. So the power to each load is VI by 2. So then we can say that if the power that is being delivered to each load is Vi by 2, then the net power that is exiting should be Vi by 2 plus Vi by 2, that is Vi. So consider that these resistors are not part of the power divider network. So therefore we can say that a single wire that is split into two different parts can act like a lossless power divider. The voltage is constant, the power is half on each branch because the current becomes half. So therefore, this is the first step to a lossless power divider. So as we said that as per this discussion, net exiting power is Vi by 2 into 2, which is Vi. So the exiting power and the entering power are the same. So therefore it is lossless. Every circuit will, or every network will have a load. So therefore there is no question of considering those loads as part of the network and therefore calling it lossy. No, not really. If you recall, in the previous lecture, while analyzing the resistive power divider also, we had essentially put loads at some of the ports for analysis. So therefore, let us try to take this concept of a wire being split into two and try to apply it into the discussion of power dividers. So the lossless power divider can be written in this way. This is a transmission line. Then we have two halves which are each going to two different ports. Let's call this as port 1, this is port 2, and this as port 3. Let us assume that the characteristic impedance of each of the port lines is some Z0. And without loss of generality, each of these connecting lines in the Y-shaped network, let the characteristic impedance of these be Z1. And this is also Z1. Now, the question is, these three sections of transmission lines are not a concern because these are essentially Z0 transmission lines which can be matched to two Z0 loads. But, so if they are matched, then the question of the length of these sections does not play a very major role, because as long as the line is matched to the load, the length can be as much as needed. So the question now is that for these two lines, the Z1 lines, what should be the length? What should be the length? Well, we know that from our earlier discussion on the impedance transformation along transmission lines, we had seen that depending on the length of the transmission line, the impedance may change. So even if the impedance at one end is real, the impedance at the other end of the transmission line can be real only under two conditions. One is if the length is lambda by 2 or if the length is lambda by 4. But what we know about lambda by 2 is that it essentially gives us the same impedance. So therefore it is not a very exciting feature, so to speak. And clearly we know that the two connections at either end of this Z1 lines are not the same. So therefore some kind of intuition tells me that it is not a good idea to keep the length as lambda by 2. Can I keep it as lambda by 4? Certainly I can. And I cannot keep any other length because then the transformed impedance will become complex and therefore there may be the question of loss or mismatch. So therefore let us consider that each of these lengths is lambda by 4. So then, before we analyze this network, let us see what we want out of our power divider. Let's say this is port 1, port 2 and port 3. So what we want is matching at all ports. That is S11 equals S22 equals S33 should be 0. Secondly, we want them to be reciprocal. So let us say 1, 2 and 1, 3, or let us say 1, 2 should be equal to 2, 1. 1, 3 equals S31. And third is that for, let us say, for an equal power divider, what it means is if there is some power input at port 1, the power will get split exactly by half on each side. So therefore, for that reason, we want S21 should be equal to S31. That is indicating the transmission coefficient. Now, what about the connection between 2 and 3? So therefore, if there is an input at port 1, it should go to ports 2 and 3. What happens if there is input at port 2? Well, if there is input at port 2, then this circuit should act like a power combiner also. That means if there is two waves which are entering, they should both get added up at port 1. That means whatever is coming in through ports 2 and 3 should go to port 1, nothing should come to the other port. Something that is coming at port 2 should go to port 1, nothing should come at port 3, and vice versa. If something enters port 3, nothing should go to port 2. So therefore, what we need is that S23 and S32 should be 0. This is called as the isolation property. This is not any characteristic with which a network is judged, but isolation is something that is desired for several circuits, especially which are 3-port or more. So as far as analysis of our networks are concerned, we shall stick with those 3 golden criteria, that is matching, losslessness and reciprocity. So isolation is a very specific property which may not be applicable to all networks. Well, having established what we want, let us now move forward and see how we can analyze this circuit. So let us say the first thing that I will do is I will look in through port 1. Let us say the impedance seen looking into port 1 is Zin, 1. Immediately I can see that there are 2 different lines which are branching. So each of them will have some different impedance. Let's call it as Zin, 1 prime for the top branch, and for the bottom branch, let's call the impedance looking into it is Zin, 2 double prime. Now, if we are looking into port 1 as per our knowledge of S parameters, ports 2 and 3 should be terminated with matched impedance Z0 if we are looking into port 1. So therefore, it is a good idea to analyze each of the arms independently first. So therefore, Zin 1 prime, that is the impedance seen at this end looking into this transmission line, that will be nothing but this impedance transformed by quarter wavelength, and that is obviously Z1 square by Z0. And because these 2 arms are symmetric, the same thing will happen for Zin 1 double prime also, that is the bottom branch. Now what is happening? Port 1 is seeing 2 impedances, one offered by the upper arm, the other offered by the lower arm. And at this junction, the 2 impedances are essentially in parallel. So therefore, the net impedance looking into port 1 will be the average, or rather, it will be the parallel combination of Z in 1 prime and Z in 1 double prime. This should be Z in 1. So this will be Z in 1 prime plus Z in 1 double prime by 2. If you apply the parallel combination formula, this is what you will get. So that will be Z1 square divided by 2Z0. This is the impedance that is looking into port 1. But if port 1 has to be matched, we should see an impedance equal to Z0. So this should be equal to Z0, that is needed for matching at port 1. Needed for matching at port 1. So therefore, with this, we can simply cross multiply and obtain that the Z1 will be equal to root 2 times Z0. So therefore, the connecting arms between port 1 to port 2 or port 1 to port 3 must be of impedance root 2 times Z0 if port 1 is to be matched. This is a very important result. This is a very important result. So therefore, if Z1 equals root 2 times Z0, that means Zn comma 1 will be equal to 2Z0 square by 2Z0, which we just derived, and that is equal to Z0. So that means the reflection coefficient at port 1, that is S11, that will be Zn1 minus Z0 divided by Zn1 plus Z0. Since Zn1 is equal to Z0, this will be 0. So S11 is 0. That we have now proved. So one parameter we have got. Now we need to find out if a wave is entering port 1, what will be the voltage at ports 2 and 3. In other words, we need to find out what is S21 and S31. So since the path connecting port 1 to port 2 and port 1 to port 3 are the same, it will be simple to just calculate any one of them and say that similar will be the case for the other one. So therefore, let's look at S21. So let's suppose at that junction, that's port 1, I'm applying some voltage, that is Vs, and it is connected to port 2 by this Z1 line, and port 2 is over here, terminated with an impedance of Z0. And needless to say, this length is L. So let us consider this as the source and this as the load. So therefore, let us put the convention of transmission line, the length variable, let's call this L equal to 0, and here L is equal to lambda by 4. So then we can write the equation for voltage and current along this transmission line. So therefore, let us say, if you are representing this as V of L and this current as I of L. So V of L will be V plus e raised to j beta L. Remember that this indicates the positive L axis. V minus times e raised to minus j beta L. And the current equation will be V plus by Z1 times e raised to j beta L minus V minus by Z1 e raised to minus j beta L. Now we can apply the conditions at the source and the load end. Let us first look at the source end. Source end is over here, that means here L is lambda by 4. So therefore the voltage over here V of L is nothing but the source voltage, which is Vs. So therefore if we substitute lambda by 4 over here in the voltage equation, then we will get Vs is equal to V plus times e raised to j beta L. So if L is lambda by 4, beta L will become pi by 2, as you well know. So therefore it will become jV plus, and here it will become e raised to minus j pi by 2, making this second term minus jV minus, and that is equal to Vs. So therefore if I divide the whole equation by j, what I will get is V plus minus V minus is equal to minus j Vs. Let's call this as equation number 1. Why I am calling it equation number 1 is because we shall get another equation by applying these equations at the load end. So let's do that. Let's do that. At the load end, essentially L is 0. So here V of L will be nothing but V plus V minus, and I of L will be V plus by Z1 minus V minus by Z1. So as you know, Z1 is nothing but root 2 times Z0. So if you substitute this, you will get V plus by root 2 Z0 minus V minus by root 2 Z0. So we know what is the voltage and current at the load end. So therefore, if I take the ratio of these two quantities at the load end, the answer will be nothing but the load impedance, and that is in this case Z0. So therefore I will say V of 0 divided by I of 0 will be equal to Z0, and that is equal to the ratio of these two quantities, that is root 2 Z0 times V plus V minus divided by V plus minus V minus. So immediately I can see that these two will get cancelled, and by doing a little bit of cross multiplication, I can say that V plus minus V minus will be equal to root 2 times V plus V minus. So therefore if I take all of these on the same side, I will get root 2 minus 1 times V plus root 2 plus 1 times V minus will be equal to 0, and this is equation number 2. So we had got equation number 1, we had got equation number 1 in the previous page, that is this. So what we can then do is observe that essentially equations 1 and 2 are a pair of simultaneous equations with the variables V plus and V minus. So if you substitute and solve, or rather if you solve this pair of equations, you will get the values of V plus and V minus. So once we get that, you can prove let me write this once. V plus and V minus. So what are we looking for essentially is the voltage at port 2. That means the point where L equal to 0. And what we saw was that V of 0 is nothing but V plus plus V minus. And you can prove that this will be equal to minus J Vs by root 2. So what is the voltage at port 1? Voltage at port 1 is nothing but Vs. So that means the S21 will be the voltage at port 2 divided by voltage at port 1, which is nothing but minus J by root 2. And since we know that S21 is equal to S31, we can say that this is equal to S31 also. Notice something very interesting. The voltage ratio in magnitude is 1 by root 2. That means if I now consider the power is nothing but the square of this. So the square of 1 by root 2 is half, which is indicating that indeed if there is some power P, half of the power from port 1 goes to port 2 and the other half goes to port 3. And this minus J indicates a phase change of 90 degrees. And that should not be surprising because the length of those two Z1 conductors is essentially lambda by 4, which corresponds to a phase change of 90 degrees. So therefore, this result should not come as a big surprise. Its ramifications are very, very clear. So far we have found out what is the S11, the S21 and the S31. So what happens is that you can do the similar analysis to find out S12 and S13 also. And you can prove that effect even they will be the same value. This is something you can try out. You can apply voltages at ports 2 and 3. This you can try it out as an exercise. Now, what about S22 and S33? So let us see what happens. What it essentially means is we have to look into either port 2 or port 3 and terminate the remaining ports with Z0. So therefore, let us look at S22. So what is happening? If I am looking at port 2, let's call it as Zin, comma 2. This is Z1, and what we know is that for this analysis, all of the other ports must be terminated with Z0. Same over here. So we know that Z1 is equal to root 2 Z0. So this impedance Z0 will get transformed into 2Z0. So effectively what's going to happen now is that at this junction of port 1, the transformed impedance from port 3 will be in parallel with Z0. So therefore, what will essentially happen over here is this is port 2 and over here we will have a parallel combination of a Z0 and a 2Z0. So the resulting combination of these two would be something that is definitely less than Z0. So therefore, the net impedance at port 1 end that will be 2Z0 by 3. So therefore, if this is lambda by 4, what will be the impedance that is seen at port 2? Simple, we just have to transform this impedance along lambda by 4 through Z1. So that means now Z in 2 that will be equal to Z1 square divided by 2Z0 by 3. And let's substitute what is Z1, that is 2 Z0 square divided by 2Z0 by 3. These two cancel out, this and this cancel out, and this is 3Z0. And by the symmetry of the situation, we can also say this is Z in 3. Or let's not call it Z in 3 right now. So Z in 2 is this. So that means S22, the reflection coefficient at port 2 is nothing but Z in 2 minus Z0 divided by Z in 2 plus Z0. And that is half. And this will be equal to S33 also, because the two connections are rather symmetric. So now we know what is S22 and S33 also. What we don't know is now S23 and S32. Now this is rather tricky. So that means if I now want to find out what is S32, if I find out what is S32, I have to terminate port 1 with Z0 and port 3 also with Z0. Now finding S32 is slightly tricky because of this connection over here. But one way to look at it is to consider that a wave that is entering port 2 is first reaching port 1 and then it is flowing from port 1 to port 3. So we know that S12, that is this quantity from port 2 to port 1, we know because of in the same way how we had calculated S21 or S31, S12 is nothing but minus j by root 2. And S31, that is from port 3 to port 1, that is also equal to minus j by root 2. So therefore, if you are applying the notion that the wave entering port 2 undergoes two transmissions, one from here to here and then from here to here, then I can say that S32 is nothing but S31 multiplied by S12. So therefore, I will multiply these two, that is minus j by root 2 into minus j by root 2, which is minus 1 by 2. This is S32 or S23 because the two are symmetric. So therefore, we can now write the S matrix for this particular network. So the net S matrix would look something like this: 0, minus j by root 2, minus j by root 2, half, half, minus half, and minus half. Now, let us see what this implies. Here it means S11 is 0, but what we are seeing, S22 and S33 are not 0. That means they are not matched. Are they reciprocal? Is this network reciprocal? Yes, it is reciprocal because this S matrix is symmetric. Why? S transpose is equal to S. What about losslessness? Well, we know that there are no resistors in this connection, So therefore it should be lossless, but then we should be able to verify it with the unitary property, that is S transpose into S conjugate. Let's do this. So the conjugate now will be so if you multiply, what we will get is one by root 2, sorry, 1 by 2 plus 1 by 2, that is 1. Here it will be minus j by 2 root 2 plus j by 2 root 2, so it will be 0. Likewise here it will be j by 2 root 2 minus j by 2 root 2, so again 0. So this way you can show that the matrix that you will get is essentially an identity matrix. So that means this is indeed lossless. So therefore what we have got is a lossless power divider or a combiner, but it is not matched. It is lossless and reciprocal, but it is not matched. Moreover, before starting the discussion on this type of a power divider, what we essentially saw was that the isolation parameter, the S23 or S32, must be 0, because there should not be any interaction. There should not be any interaction between ports 2 and 3. So what we are seeing essentially is that S23 and S32 are not 0, therefore it does not satisfy the isolation property. Isolation property is not satisfied. So what to do? What to do? We are back to square one. We are just a little bit happy because we found out one way with which we can make the power divider lossless. But what we are seeing is that we are in that process, we are losing the matching criteria. Only port 1 is matched. The other two ports are not matched. And matching is something that we really want. So therefore, there was a scientist, an American scientist by the name E.J. Wilkinson, who proposed a solution for this problem. He said that by making a simple modification to this existing lossless power divider, we can make all the ports matched, and at the same time we can divide or combine power in equal ratios, and we can also achieve isolation between ports 2 and 3, that is S23 and S32 will be 0. This is the claim which he made, and this invention of his took the community by storm. And that invention was called as the Wilkinson power divider. That is the Wilkinson power divider. So what he started with was the exact same thing which we had started with for the lossless power divider. each of these conductors is lambda by 4, and each of this is Z1, port 1, port 2, port 3. The feed lines for each port is Z0. But the change which Wilkinson made was, he said, connect a resistor between ports 2 and 3. This was the change which he proposed. So he also said, for sake of simplicity, you can assume that the second conductor is ground, which we have also assumed in some of our analysis. So all that Wilkinson said was, add this resistor. Add this resistor. So immediately what we can say is that because of this added resistance, the circuit is now lossy. So again, it seems that we are back to square one. What we were trying to do so far to essentially work around the loss, that seems to be gone. But no, here comes the catch. Wilkinson said that the loss will be used in an advantageous way. That is, there will be no loss while going from port 1 to port 2. There will be no loss going from port 1 to port 3. Likewise, there will be no loss going from port 2 to port 1. No loss while going from port 3 to port 1. The only place where this R will play a role is the signal transmission between ports 2 and 3, because it is connected between ports 2 and 3. So now, if this resistor is placed in such a way that there is no transmission between ports 2 and 3, that means there will be a perfect isolation. There will be nothing, no wave flow between ports 2 and 3, and that is precisely what we want. So Wilkinson tried to justify this in a different way. So let us say, we'll say now the top view of the WPD. So the short form for Wilkinson power divider is WPD. So let us now look at it from the top side. That is, the bottom conductor or the ground conductor will not be visible, but we'll assume that it is there. So therefore, this is what it looks like. This is lambda by 4, and so is this. Port 1, port 2, and port 3. So another way in which Wilkinson tried to explain his theory was that he said, let us suppose a wave is starting from port 2. To reach port 3, it can see two ways. One way is through this resistor. The other way is through this long path. Both can happen. Now the thing is, when the wave passes through this resistance, if you assume that the resistance is small enough, then the phase change or the electrical length theta will be 0. Of course, the catch is the size of this resistance should be quite small, or much smaller than the wavelength. On the second path, if you are going from port 2 to port 3, you first go from port 2 to here, you get a phase change of 90 degrees, and then one more change of 90 degrees. So therefore, in this path, the phase change would be 180 degrees. So what we are having at port 2, 3 is, because of the input at port 2, there are two waves now. One with no phase change and one with a phase change of 180 degrees. So we are essentially having two signals of opposite phase. So if we can ensure that their magnitude is equal, then they will cancel out at port 3. So with this logic, Wilkinson tried to support his claim of using the loss in an advantageous manner. that is to achieve no connection whatsoever between ports 3 and 2 or 2 and 3. But we have a problem. This kind of analysis, just doing it superficially, is not enough. We need to understand whether indeed S23 or S32 is becoming 0. The second problem was whether S22 and S33 are both 0, that is whether ports 2 and 3 are matched. These are the questions we have to answer. But this triangular looking structure is a little difficult for us to analyze. Unlike the previous case when this R was not there, the analysis thus far was quite simple. So, to analyze this kind of interconnected structures, we will make use of a different approach. And that approach is based on a certain technique which we will learn in the next lecture. Thank you.